Good day everyone. In this lecture we're going to revise some mathematical concepts and also introduce some new concepts that we will be using through the course. So these are tools that you must know since we are going to rely on these tools later on. So firstly I want to refer you to your data sheet. Now this document you must have with you at all times, because you are constantly going to refer back to this document. You will also be given a copy of this document in the tests and also in the exam. So please familiarize yourself with where certain pieces of information are given in this document. So if you look at the beginning of the data sheet, on the first page you will find some constants with their units given. There are also some conversions for specific units, joule, pascal, electron volts. Then there are some useful mathematical relationships. For example, I squared equal to minus 1. The relationships between cos and sine curves. Then there are some derivatives that we're going to use. On the next page you will find some integrals, and then from page 3 there are equations relating specifically to the chapters that we will be looking at. Okay, so the first concept that I want to define is a new concept. Some of you may have heard of this, and that is the concept of dimensionality. So we will be referring to the idea of dimension throughout the course. So there are different types of dimensions that we can define. When we talk about something being a single point, that would be 0D. A line is referred to as a one-dimensional system, and that we would typically refer to as the x direction. A two-dimensional system is like a sheet, so a page would be a 2D system. And then of course the 3D system is your typical Cartesian coordinate system, the three-dimensional world that we live in. So for the 2D system we use the x and y coordinates, and then for 3D x, y and z. So when I talk about a 0D, 1D, 2D or 3D system, this is what I would be referring to. Then some other mathematical relationships that we're going to come across. If you think back to maths, the symbol I, that is the special symbol where I squared is equal to minus 1. Just think about this relationship. Minus I squared would be minus I times minus I. And remember, a minus times a minus would give you a plus I squared, which would again be minus 1. So we're also going to use that. Okay, so let's have a look at some derivatives. Just some general derivatives. If you have a look at your data sheet, that one there, we see is a constant. We generalize the derivative to x, it can be any symbol. C is a constant, the derivative of a constant is 0. So dx of a constant is 0. ddx of x is 1. Another derivative that you might find useful in your data sheet. d dx of x to the n is n x to the n minus 1. We have an exponent. Okay, and then some other functions with exponents. Let's look at that one in your data sheet. d dx of e to the kx, where k is a constant, is k e to the kx. So the constant is in the derivative in front of the function. So you have the function repeating, but you also multiply by the constant k in the function. So let's look at that one. d dx e to the kx is k e to the kx. So that function times the constant. So k is a constant. Then there's another form of this function which is a bit more complex, the one below it, where your function is e to the ikx. So you have an I in front of in the exponent. The derivative is very simple because it's similar to the one we've just seen. We again have the constant where I is included in the constant. So instead of having just k multiplied by the function, you have ik multiplied by the function. So d dx of e to the ikx is ik e to the ikx. So it's the same rule that applies. You just use the I as well. Ik e to the ikx. Again, k is a constant. Okay, so let's look at a more complex example where we are actually going to use this relationship. So I give you this function. And I tell you A, B, and K are constants. And I'm asking you to calculate the second derivative of this function. Now the first thing you'll notice is that our function is a sum. This is something we haven't talked about, but if you look at your data sheet, there is the key, the derivative of a function fx plus gx, where you have a sum. You just get the derivative of the first term of the sum plus the derivative of the second term of the sum. So d dx fx plus gx is d dx of fx plus d dx of gx. So that's the derivative of a sum. So going back to our question, we want to calculate d squared dx squared of our function, which is a e to the ikx plus b e to the minus ikx. So getting the second derivative is the same as getting two first derivatives. So d dx a e to the ikx plus b e to the minus ikx. So let's get the first derivative. Now the first derivative is the same as splitting the derivative over both terms. And you'll notice that I included a lot of detail in these calculations. You don't have to include all these steps if you can do this in fewer steps. This is just to show all the detail. And going back to the rule that we've just defined, or just to include one more step here, I can take the constant out. Okay, and the d dx is over everything, the second derivative. So now we can use our rule. d dx of e to the ikx is ik e to the ikx, plus, in that case, d dx of minus e to the minus ikx would be minus ik, because that's our constant, e to the minus ikx. So there we have the first derivative. Now we have to get the derivative again to get the second derivative. Now we can split the derivative again. So I'm going to take this constant. That's my constant. Out as a factor. d dx of e to the ikx is ik e to the ikx. d dx of e to the minus ik is minus ik e to the minus ikx. So here we have I times I is I squared, k times k is k squared, e to the ikx, plus b minus ik times, minus I times minus I is minus I squared, k times k is k squared, e to the minus ikx. But remember, minus I squared is I squared is minus 1, so that becomes a minus 1 times a squared. And we also said previously that minus I squared also becomes minus 1 times b, so that becomes a minus b k squared e to the minus ikx. You'll see that we have k squared as a common factor, and we also have minus 1 as a common factor. So if we take out minus k squared as a factor, it becomes a e to the ikx plus b e to the minus ikx, which is the function that we started off originally with, a e to the ikx plus b e to the minus ikx. So this is just minus k squared fx. So there we have the derivative of the second derivative of the function fx. It's just minus k squared of that function. Some additional relationships with regards to derivatives that I just want to point out to you. When you have a product of two functions and you want to get the derivative of the product, the first function times the derivative of the second function plus the second function times the derivative of the first function. Got a dx there. That relationship is also given in your data sheet. When you have two functions that are divided by each other, it's a bit more complicated. In this case, you write down the bottom function first and you multiply that by the derivative of the top function. Subtract from that, write down the top function first, multiplied by the derivative of the bottom function. All of that divided by the square of the bottom function. Again, these two ways of getting derivatives are given in your data sheet. There's the one for two functions that are multiplied, and there's the one for two functions that are divided by each other. Next, I want to have a look at the sine and the cosine functions, as we're also going to use these functions. Our x-axis is going to be defined in radians. So we're going to use values like pi, 2 pi, or n pi. So when you want to calculate a value, make sure that your calculator is set to radians. So let's first look at the function sine x. So if you were to plot this function, that is our x-axis, +1, -1, that is x equal to 0. At x equal to 0, the sine function is 0. And it then repeats with a period equal to 2 pi. So at 2 pi, it is again 0, and it has a full cycle. At pi radians, x is also 0. Sorry, the sine function is also 0. At pi over 2, it is 1. And at 3 pi over 2, it is equal to -1. And of course, it repeats on the other side of the 0 value on the x-axis. So that would be -pi, -2 pi, pi over 2, -3 pi over 2. So you must know the shape of the sine function. The second one is the cosine function that you need to know. Again, this is the x-axis, 0, +1, -1. And in this case, at x equal to 0, the cosine function is +1. And it is symmetric about 1. It again repeats over 2 pi radians, and at 2 pi it is again equal to 1. So at pi over 2, it is equal to minus 1. At pi it is 0, and at 3 pi, sorry, at pi over 2 it is 0, 3 pi over 2, sorry, that should be pi. 3 pi over 2, it is again 0. So 0, pi over 2, pi, 3 pi over 2, 2 pi. And the same on the other side, minus 2 pi, minus pi, minus pi over 2, minus 3 pi over 2. So these two graphs you need to know the shape of, and you need to know the values at the specific points. The reason why we need to know this is because we're going to use this when we calculate integrals. So let's have a look at some examples for integrals. So if you look at the second page on your data sheet, this is where you will locate the integrals. Just like derivatives, I will never give you an integral that is not on your data sheet, so you don't need to memorize any integrals, you just need to be able to find them on the data sheet. So let's look at our first integral. So the first one that I want us to look at is this one, the integral of sin x over the region 0 to 2 pi. Okay, so you don't need to memorize this, you can just go to your data sheet, to the section under integrals, and if you browse through this you will find that relation that says integral of sin ax dx is minus 1 over a cos ax. Now in this case it is not exactly the same as the equation we have, but we can still use this. So from the data sheet we can find so if we imagine there to be a 1 in front of the x, we can just make our a 1. So with a equal to 1, this integral in the data sheet becomes 1 over 1 cos x. So it is equal to minus cos x. So the integral of sin x dx is minus cos x. Okay, so let's go back to our question. We want to integrate over the region 0 to 2 pi sine x dx. So remember, when you do an integral you use that and you integrate over this region. What you then do is you first substitute the 1 limit for x, and then you minus, and then you substitute the second limit. So minus cos of 2 pi. So if we go back to our cos graph, cos of 2 pi we said is equal to 1 minus 1. We have another minus. That minus cos of 0, cos of 0 we said is also equal to 1. So minus 1. So that's that minus, cos of 2 pi is 1, minus cos of 0 is 1. So it's minus 1 minus times a minus is a plus 1, gives you 0. When you do a calculation, always ask yourself if the value makes sense. So we're integrating over the sine function. Remember, integration is determining the area of a function. integrating over sine x from 0 to 2 pi. If we go to our sine function, we've integrated, we've determining the function and the area under the function from 0 to 2 pi. So there we've got a positive, negative, cancels out. So it should give an answer of 0. So yes, our answer makes sense. Okay, so let's have a look at a slightly more complex integral. We're going to integrate between the limits 0 and L, where L is just an arbitrary constant. The square of the sine function, n pi x over L dx. And I tell you that obviously pi is a constant and L are constants and n is an integer. Okay, so if n is an integer and pi and L are constants, then n pi over L is a constant. So we can say n pi over L, let's make that a constant a. So effectively our integral becomes this, a times x dx. So if you look at your data sheet, you will find that there's an integral for that function. Integral of sine square ax dx is x over 2 minus sine 2ax divided by 4a. So for that, the general integral is x over 2 minus sine 2ax over 4a, where a is equal to n pi over L. So if we go back to our integral, our question, we know that that is equal to x over 2, a in this case is n pi over L, we still have the x, divided by 4a, which is n pi over L, between the limits 0 and L. So all that we need to do is, for this quite hairy term, first replace x with L, and then subtract from that the term where we have replaced x with 0. So let's do that. Firstly, replace x with L. L over L. Minus, then we replace x with 0. All of that divided by 4 n pi L. So that becomes L over 2. Those L's cancel. Minus 0, minus times a minus becomes a plus. N times pi times 0 just becomes sine 0. Okay, so here we can again refer to our sine graph. Because we said that n is an integer, so that would be 0, 1, 2, 3, etc., a whole number. When n is 0, that becomes sine of 0. When n is 1, it becomes sine of 2 pi. When n is 2, it becomes sine of 4 pi. And we know that the sine curve repeats every 2 pi. So when n is 0, we're sitting at 0. When n is 2 pi, the sine function is 0. When n is 4 pi, it will repeat again, it will become 0 again. So the sine function of n times 2 pi, when n is an integer, becomes 0. So this whole term becomes 0. And the sine of 0 again becomes 0. So this whole function becomes L over 2, because these two terms just fall away because of the sine function and the fact that we've defined n as being an integer. So this is an example of a more complex integral, and it also illustrates how we use the shape of these sine and cosine functions in our integration. Okay, so this is a summary of some of the tools that we will be using in this